No. Okay. Better. Angles. How's that? Is that close enough? Good? Great. Okay, thanks everyone for coming. Today I'm going to talk about some work in creating domain-specific procedural systems for creative production. The previous talk of the title was domain-specific programming tools for creative production. I'm going to get into why it's slightly shifted. But before I start, just a little bit about myself and where I'm coming from. So I'm a postdoctoral scholar in computer science at Stanford University. Specifically, I'm a fellow in the Brown Institute for Media Innovation, which is a cross-disciplinary, cross-institutional institute between Columbia University and Stanford. Before joining Stanford, I did my PhD at the MIT Media Lab. And broadly, what I do now is HCI, or human-computer interaction research. So I collaborate a lot with folks in programming language research and graphics research, and I focus primarily in my own work on building systems and evaluating those systems with different types of creative practitioners. And generally, when I give talks about this work, I'm speaking often to purely academic audiences or audiences of designers or artists or other types of creative practitioners. And so since programming is one of the most creative fields I'm aware of, this shouldn't be a stretch in any respect. So let's get started. So computer programming has given rise to new forms of art, specifically procedural art, which is this very broad area of creative practice where artworks are described as a series of computational rules, models, relationships, or instructions, generally in the form of a computer program. And before I go any farther, I should also clarify what I mean by the term artist. So in this talk, I'm using the term artist to refer to a broad set of practitioners who are invested in using programming to create artifacts that often have some form of aesthetic focus, but also may be provocative, reflective, exploratory, and then also potentially have some practical applications. So this can include a broad variety of different types of practitioners from areas that are either intersect with art or sometimes are viewed as outside of art: craft, engineering, musicians, graphic designers. And this definition has kind of come out of my experience in looking at the different types of creative practitioners who are using programming and how they're using it, and the different genres in which they fall into. So procedural art offers many distinct creative opportunities. Among other opportunities, art created with code can be autonomous, it can be dynamic and responsive, and it can be generative, meaning that it's capable of producing novel works that are not explicitly conceived of by a human artist. The artistic potential of programming, sorry, one second. Other side, okay. Oops. Minor technical difficulties. How's that? Can you hear me? Okay, all right. The artistic potential of computing is mediated by the design and structure of different programming tools. And building effective programming tools for art is challenging, just like building effective programming tools is challenging. But part of the challenge when it comes to art stems from the nature of human creativity. So human creative production is highly complex, multifaceted, and different people... Great. All right. Okay, so as I was saying, human creative production is complex and multifaceted, and different people are creative in really different ways. So the core attributes of creativity itself are really elusive to define. They're very difficult to measure, which makes my research particularly challenging. And they're all, as a result, really challenging to embody in computational tools and systems. The challenges posed by the diversity of human creativity are compounded by the restrictions and gaps in existing mainstream programming tools and computational tools traditionally targeted at artists. So a lot of procedural art today is performed through textual languages that are specifically built for art practitioners and designers. So these are generally creative coding libraries and APIs, some of which contain custom programming environments. And there's a lot to like about these tools. Two notable examples here: Open Frameworks, created by Zach Lieberman, Theo Watson, and Arturo Castro, and Processing, which is one of the earliest versions of a textual creative coding language for artists, created by Casey Rees and Ben Fry. And one of the best things about these tools, and one of the reasons they exist, is that they're built by open source communities of passionate people who really care deeply about supporting the creativity of others. And they're also built by people who are artists themselves. And another thing that's great about these systems is that they're extremely expressive in one sense, because they extend general purpose programming languages like Java in the case of Processing and C++ in the case of Open Frameworks, which means that you're not limited to the language itself, but you have a general purpose programming language you can build on top of. But this expressiveness also poses a challenge, because like the general purpose languages upon they're built, these languages require knowledge of textual programming conventions and contain lengthy method sets and APIs, which can be great if you're an experienced programmer, but if you're just getting started, these tools often require you to learn a great deal before it's possible to produce original results or interesting results. And so one common problem in this space is that artists who are new to this field can often resort to reusing example code with minor modifications or sort of unstructured modifications, which really limits the creative diversity that's produced by new entrants to this space. Another limitation of these tools is that they can limit key forms of artistic practice and expression by requiring artists to work exclusively through a representation, rather than enabling them to work on the concrete artwork itself. And this is a point that, if any of you are familiar with Brett Victor's work, he addresses this a lot in some of his presentations. Contrasting to this, digital direct manipulation tools suggest alternative forms of computational creation because they enable creators to manipulate digital artifacts through continuous, concrete control and immediate visual feedback. And these tools demonstrate how it's possible to create computational tools that support forms of control that are really similar or influenced heavily by traditional forms of manipulation in the physical world. But most direct manipulation systems don't provide the same level of computational power, control, and expressiveness that programming does, and they can't produce the same types of dynamic outcomes and relationships. So the third category is visual programming languages. Who here is familiar with visual programming? Okay, great. Visual programming takes a lot of different forms. There's a lot of different design patterns and structures in visual programming, but in general, it can offer a more approachable entry point than purely textual languages because you don't have syntax errors. And visual programming can also be more discoverable. Often the components of the language are presented all in view within the editor, as opposed to having to look through some external documentation. And the design of the blocks themselves often indicates how they're supposed to be put together, so it can encourage risk-free exploration in ways that textual languages don't. And visual programming languages as a whole represent a really important step in making programming more approachable. But it's important to point out that visual syntax alone doesn't address the challenge of leveraging computation for creative tasks. And as kind of one important example, many visual languages can be as challenging to debug as textual languages. And another fact about visual languages, they still impose the separation between the artist and concrete manipulation of their work because they're still acting as a representation of the work itself. And I'll talk more about visual languages later on. So the objective of my research, in light of the creative opportunities of programming contrasted with the restrictions of some of these existing tools, is to broaden the creative potential of computing by developing procedural systems and programming systems that support professional artists across different disciplines, communities, and cultures. And my approach is to develop new entry points in the form of domain-specific tools, languages, interfaces, and frameworks that enable artists to apply computation to deep and original creative works and practices. Today I'm going to be talking about two specific systems I've built that focus primarily on the domain of visual art. And my research builds on efforts in end-user programming and learnable programming research, but with the distinct goal of supporting professional creative practitioners from domains that are traditionally separate from programming. So this has meant working with people who range from oil painters to fashion designers to traditional craftspeople, but it's also included working with people who already rely on digital tools but don't program, for example, graphic designers. And I work to identify commonalities and opportunities for pluralism between procedural and traditional practices, and then develop tools that embody qualities of both of these spaces. And this plurality is demonstrated through the work created by professionals using the systems I've built, which blend procedural affordances with traditional aesthetics, and also demonstrated through the experience that artists have in using these tools. So this is one artist from a study I conducted describing how using the system was similar to her experience working with oil paint, where she said, "I feel like I can start with a blank canvas and then I can find something. A lot of how I work really resonates with this. You can create some parameters and you don't know exactly what it's going to be, and that's great. You can build a process in an organic way." I researched the development of new tools through this process of interdisciplinary systems engineering, in which new computational tools are motivated through an understanding of real-world creative practice, developed by people with experience in both artifact production and engineering, refined through practical application in the process of actually making artwork, and then evaluated with real practitioners based on the diversity of outcomes they enable. And this process subsequently motivates future systems. And the approach that I take to building systems corresponds with the structure I'm going to take in the remainder of this talk today. So I'm going to start by briefly talking about the results of need-finding research I've done with artists, and then move to describing a system I've developed for bridging procedural manual practice informed by this need-finding. Then I'll describe the approach I took to evaluating the system and talk about some of the opportunities that this demonstrated and also some of the limitations it pointed out. And then talk about how the limitations raised by this evaluation led to a second slate of need-finding research aimed at more precisely understanding strategies that artists might take when combining a specific form of manual practice, in this case drawing by hand, with computer programming. Then finally, I'll talk about a second system that was inspired by this, a meta tool for allowing artists to develop their own computational tools for creative production, and the approach I took to evaluating this work. And I'll conclude with some general takeaways about, based on general principles this work demonstrates. So my work overall is built on a foundation of recorded interviews, studio observations, and structured collaborations with different kinds of artists. And in conducting this work, I've made an effort to select artists who work in both traditional and emerging fields and who use different tools and media. And in fact, this last picture here is actually the conference I just came from in Thailand on the way to this conference, a conference called Digital Naturalism, which was a collaboration between artists, engineers, and scientists looking at different forms of applying technology to biohacking and hacking in the wild. So broadly, I conduct need-finding studies through three lenses of practice: learning, process, and expression. And today, there's a lot of information I've gained through this research, but I'm just going to touch on a few key points that have motivated the systems I'll be presenting today. So programming, in part, is a skill, and therefore, like any skill, learning it takes time and effort. But for anyone who's worked extensively with artists or is an artist themselves, you know that artists regularly invest time and energy in learning new things. It's part of what being an artist means. But in addition, learning itself is complex, and learning tools involves additional dimensions rather than just how hard or easy something is. It also involves the types of learning styles that are encouraged by a given field or a given tool. So with respect to these ideas, I tried to examine what specific challenges artists encountered when first learning programming tools. Some of the subtleties of computational learning challenges were revealed through my interviews with visual artists. And this is a quote from Nina, who's a printmaker, who talks about her reluctance to invest energy in learning the creative coding framework processing due to her view of the aesthetic limitations of these systems overall. She said, "When I start playing around with programming tools, what I come up with or what happens visually is so clearly novice that it doesn't interest me." She further elaborated how she's more interested in learning technical tools that aren't just a visual end into themselves, stating that she wants to be able to do something personal with the system she uses. And Nina's comments here were echoed by many other artists I spoke with, and they illustrate this larger impression that many artists have of programming tools as a domain with enormous potential, but with systems that are brittle, difficult to get started with, and hard to reconcile with their initial creative goals and learning styles. So another question I examined in my need-finding research focused on process. Specifically, how do different procedural tools or programming languages hinder the workflows of different artists? And a common theme here was the importance that manual artists placed on the direct connection between their hands and their work. So Chantel, who is a visual artist who creates large-scale drawings and murals, compared her experience with programming to her experience with drawing. She said, the way that we code or the way that we program, it's not gestural, it's not physical. I'm very head-to-hand when I'm creating. And as Chantel's quote indicates, her direct contact with them and direct contact with the piece was central to her form of manual practice, and this is true for many forms of manual art. And so there are different creative opportunities presented by representational and concrete manipulation. And the distinction between these forms of manipulation is important because concrete manipulation offers different pathways, both for learning and creating, and it can support different creative outcomes. So this idea of bridging the opportunities of procedural creation with the workflows and learning styles of manual artists led to a specific research question. Can we support approachable and expressive procedural art creation by enabling artists to describe procedural relationships through direct manipulation? So to explore this question, I augmented the conventions of graphic art software to create Para, which is a system that supports the creation and modification of procedural relationships exclusively through direct manipulation. And this is work done in collaboration with Joel Brandt, who's now at Snapchat, and Radomir Mek, who is at Adobe Research, and Sumit Gogia. For those of you who have built software or programming frameworks are aware, with any computational system, you're constructing, well, specifically to software, you're constructing at least two primary components. A model, a representation of the types of computational relationships you can express in the system, and an interface, the mechanism through which those relationships are expressed. So in designing these two components, there's several parameters that I'm trying to optimize for. Ideally, I'm trying to create interfaces that are approachable, that are discoverable, meaning that their components can be found independently without external aid or references, and that are scalable, meaning that they can scale to the creation of complex works of art. And then in this particular case of Para, concrete. Similarly, there are a common set of goals for designing programming models, particularly for people who are new to programming. A lot of this is coming out of learnable programming research. So selecting the right number of primitives and selecting a small number increases the likelihood of the system being approachable, but also selecting primitives in a way that still enables a high ceiling or the ability to express complex things. And then finally, in our case, also selecting primitives that enable diversity so that many different things can be created with the same building blocks. And these two components have to support one another and they have to be developed in tandem. So to talk about concretely how this was employed in Para, Para's interface was developed as vector drawing software because it enabled the interface and interactions to closely resemble software that was already being used by manual artists, tools like Adobe Illustrator, Inkscape, or OmniGraffle. And the interface features analogs of elements in digital vector graphics illustration software, like a layers panel, a toolbar, color picker, things like that. Para's procedural functionality is structured on a declarative model, meaning that it supports the expression of logical relationships, but doesn't require the artist to describe the control flow explicitly. So Para extends the conventions of vector drawing software with three primary components. The first is declarative constraints, ordered lists, and declarative duplication. And we used an iterative process to arrive at these components and design them in a way so that they enable recombination in different ways to support different outcomes. So to illustrate how this works, I'll walk through each of these components in order and describe on how they build on one another. So in general purpose programming languages, complex relationships are often comprised of low-level operations. And Para builds on this approach through object-to-object constraints, which are the fundamental building block for more advanced procedural functionality in the system. Constraints let an artist maintain geometric and stylistic relationships in a drawing by enabling them, by enabling them to select two or more objects with the constraint tool, which then pulls up a constraint creation interface, which is shown here. And this example shows using one-to-one constraints to maintain relative relationships in fill color on the portions of this flower. So as the center portion is modified, it simultaneously affects the outer portion, which has been constrained to it, in a relative relationship. Textual procedural tools often enable the management of multiple objects through abstract data types, like lists and arrays. And similarly in Para, lists are sort of serve the same approach, with the exception that they're visually represented, ordered collections of artwork that can be procedurally manipulated. So one list can be used to scale a single constraint to many objects. So it's an example of the flower here, by using a list to store all of the outer, darker segments of the petal and then constrain them to the center portion. You can apply one constraint to all of those objects simultaneously. But Para also enables new types of constraint behavior to be created through lists. So lists can also support iterative variation in forms that are similar to the types of variation enabled through loops and textual tools. In this example, the shapes of this repeating pattern are constrained on the x and y axis by a list of two ellipses. And what this does is it creates a relationship where the constraint produces an iterative behavior where each object inside the relative list is constrained differently based on a set of values calculated from the objects in the reference list. So if there are more than two objects in the reference list, it's possible to produce a nonlinear distribution, in this case creating a curved distribution of the pattern. So essentially what's happening here is the reference list objects, these three ellipses, are acting as control points for modifying this collection, this list of diamonds and ellipses. Using the constraint panel in the system enables modifications to a constraint behavior to produce other variations. So for example, specifying a radial iteration, which calculates values based on a radial distribution, with the diameter described by the first and last member of the reference list. And overall, constraints and lists facilitate procedural relationships, but they can't generate new objects by themselves. But a great deal of procedural art also requires the ability to automatically produce new forms. So we added duplicators to Para to enable this form of generativity. And basically, duplicators are just specialized lists with the ability to declaratively control the number of objects they contain. So duplicators consist of a set number of copies of an object with an internal iterative constraint on the collection of copies, with the first and last copy serving as reference. And this enables iterative changes on any property by modifying the first and last objects, and updates to the number of copies preserves these constraints. So to kind of demonstrate this in greater detail, I'll show a practical example where a star field is generated by using duplicators on a single star drawing, and then the last star in the duplicated set is scaled up to produce a variation in size. Then the distribution of the position constraint is set to random, which produces a set of random positions, randomly positioned stars across the canvas. And it's set for both the X and Y position constraints. And then moving the position of the outer star will automatically recalculate the random distribution. And duplicators are structured so that updates to the path of any one object will then in turn update the paths of all the objects within the duplicated collection. Duplicators can also be created on geometric groups of objects, which enables more complex distributions. And once again, constraints and collections are used to iteratively transform each duplicate and maintain geometric correspondence between each group copy. So describing the development of Para leads into what I found to be one of the most challenging aspects of building procedural systems for artists, which is understanding their effectiveness in the context of real-world practice. And this challenge for me is primarily manifested between the tensions in designing creative tools and actually making creative works. And this is because there are different mindsets involved in making tools and making work. Producing work often involves refining a singular creative goal for a specific purpose, whereas building a tool requires understanding how functionality can be scaled or generalized for different applications. And so, to examine how we actually tried to tackle this challenge of understanding Para's applications in real-world artistic practice, I'll describe two approaches we took to actually evaluating Para. So our evaluation of Para had three objectives: understand the learnability of the system, understand the specific practices that were supported or hindered by it, and to understand the expressiveness of the system in both the context of manual art and procedural art. And we tried out two different methods of evaluation. The first was a breadth-based study where we conducted a workshop with multiple professional artists, in this case, 11 artists. And this was aimed at looking at the trade-offs between our approach of direct manipulation and textual tools like processing by comparing Para and the textual tool processing. So we introduced participants to both systems and provided them with time to learn the systems, gave them support, and also gave them open-ended time to create work with both systems. And the workshop demonstrated that participants did find Para more intuitive to use than processing, and they're also able to use it independently to make designs comparable to what they were able to create in processing. But the short time frame meant that, and also the extensive time we spent instructing participants in processing, meant that people had a relatively short amount of time to use either system to generate their own art. So we didn't really have a good understanding of how Para actually performed in extended practice. So we built on this study to perform a second study that was targeted at this objective. For this study, we commissioned a single professional manual artist, Kim Smith, to use Para for 2 weeks. And after initial training, we met with her regularly over the course of the study to review in-progress artwork and discuss her experience. And we also collected data through written reflections and automated surveys or experience sampling within Para, which I don't recommend. It's very annoying to have your software ask you how you like it. And then we also piloted this approach with Para, but it's something that I'm continuing to use in ongoing work because of the unique opportunities it offers. So some of the opportunities of this, actually, I'm going to skip through this for sake of time, move directly into the results. So looking at what actually happened, there we go. Kim used Para to create a variety of different abstract pieces in the first week of the study, and she produced them by drawing vector shapes in Para and then used duplicators and constrained lists to create multiple copies with iterative changes in color, scale, opacity, blend mode, and position. But interestingly, in addition to the abstract work, in the second week, Kim used Para to create floral and animal illustrations, and she used duplicators and iterative variation to produce texture and patterning in the illustrations. And analysis of both studies revealed there were a wide variety of different creative opportunities that came out of this approach, but I'm going to focus on 2 key points today: the compatibility of Para with established skills, and also the capacity of the primitives we chose to support diverse outcomes and enable important design practices. So we built Para on this idea that direct manipulation, procedural manipulation, would enable artists to leverage existing skills. And there were a couple points of evidence that supported this. First, there were clear stylistic similarities between Kim's prior work in oil and the work she created in Para, despite being produced with different tools. And second, both Kim and the participants in the workshop described the system as intuitive, enjoyable, and familiar, in contrast to their experience with textual programming tools. So in addition to supporting easy entry, the intuitive qualities of systems like Para are important in a creative sense. People who think through movement, intuition, and visual impression can be more expressive with computational tools that validate these mindsets. The studies also enabled an evaluation of the creative expressiveness of the 3 procedural components we used in Para. And a common trade-off in tool design is that the easier tools are to get started with, the less expressive they become. But the results of our study demonstrate that Para's small number of procedural constraints, or procedural components, did not prohibit expressive creation by professionals. Rather, it offered distinct creative opportunities. So duplicators, constraints, and lists enabled artists in the workshop to produce procedural forms and patterns comparable to those created with textual tools. And Smith's illustration demonstrates parametric modulation in color, scale, and rotation across repeated forms. And her illustrative abstract work contains generative forms and patterns. But more importantly, unlike the processing sketches, Kim was able to apply these techniques to the creation of illustrative forms, not just abstract work. So with the context of this conference in mind, one question that might be raised at this point is, does Para even qualify as programming? And by design, it's true that Para does not require the artist to manipulate a symbolic relationship, which is a factor that distinguishes it from most existing coding languages. But it's also important to point out that Para represents one approach in a number of systems that enable artists to manipulate procedural relationships through direct manipulation. Some are very old and some are new. And while lacking in the qualities of traditional symbolic languages, these tools enable and often require creators to think procedurally and to think abstractly. And so when considering this space of tools, I feel sometimes it's less useful to argue whether or not they qualify as programming, and more useful to consider the new forms of thinking and working they enable, and the domains in which this approach is effective, and the domains in which it's maybe less effective. So to that point with Para specifically, Para demonstrated that with the right direct manipulation interface, it's possible to support professional visual artists in expressive forms of procedural creation while preserving manual illustration practices. Yet, as the interviews demonstrated, manual and procedural art are these broad domains with many different dimensions. And so while Para focused on the issue of integrating concrete engagement with procedural creation, there are many other aspects of both manual and procedural practice that it does not address. And while it's true that the representational nature of programming can create a barrier for some forms of manual creation, it also offers important creative opportunities, namely in the form of reflection, because code can simultaneously serve as a functional object and also as a record of an artist's ideas and processes. And being able to read and reflect on this representation has practical benefits for debugging and sharing work. So some of my earlier conversations with manual artists stressed the unique styles and variations that emerged from the physical act of drawing. But Para's use of vector graphics, while well matched to creating discrete declarative constraints, lost a great deal of this aesthetic expressiveness of working by hand. So along similar lines, our interviews also suggested a disconnect between the primitives of common creative coding languages and the aesthetic concerns of manual artists, where creative coding tools often focus on the manipulation of simple geometric forms, which can be highly expressive when combined in complex ways. But they're often not well matched to the aesthetics that emerge from practice manual control. So building on this idea, I conducted additional need-finding research that examined forms of expression that procedural manual artists valued within their respective practices. So the connection between manual control and expression came up repeatedly when talking with painters, illustrators, and people who work by hand. This was a comment from Michael, who's a studio artist, who described how his work was defined by the manual deviations in his lines. So when you looked closely at his drawings, his work was riddled with wobbles or whatever was going on in his head at the time. And it was interesting because I also spoke with procedural artists who coded every day. And not only did they actually had a lot of the same criticisms that manual artists had, where they expressed dissatisfaction with the flat, predictable quality of computationally produced forms. So to look at how some procedural artists are getting around this tension, I interviewed artists whose work contained line qualities similar to those found in manual art, but was produced with code. And I discovered in these interviews that often the approach procedural artists took was to create their own software tools that let them integrate drawing by hand with procedural styles or effects they had designed. This is a representative sample by the artist Eric Natsky, where Eric creates custom software that lets him draw freely with a digital stylus, while the software modifies the color and quality of his strokes by referencing different input data. In this case, he's sampling from bitmap images to change the color of the lines. So our need-finding research demonstrated in this case how programming languages and interfaces, while highly expressive in some contexts, can be poorly aligned with the forms of expression that are important to people who work by hand and work through drawing. And they also revealed how experienced procedural artists circumvent these limitations by building their own tools. So this led to the idea that we could aid manual artists in integrating procedural manual creation through a meta tool or a system for building tools. So this is the resulting system, Dynamic Brushes, which is a visual programming and direct manipulation drawing environment that enables the creation of ad hoc drawing tools that transform stylus inputs to procedural patterns. And developing Dynamic Brushes required augmenting the original objectives from Para, in that we had to develop a new computational model that was compatible with manual drawing, and also develop an interface that supported both tool creation in the form of programming and artwork creation in the form of drawing. So to talk about how we actually address these requirements, I'll now walk through the system. Programming in Dynamic Brushes is structured around the creation of brushes, which are interactive drawing objects that respond to manual input from the artist. And each brush object has properties that define the style and geometric transformation of its strokes. The programming model is centered around three core constructs: property mappings, which are declarative mappings between input data and brush properties. And the primary form of input in the system is stylus properties, so stylus position or stylus force or stylus angle. But mappings can also use generators, which are another type of data type as input that produce a sequence of values corresponding to a given function. So for example, modulation with a sine wave. Mappings are organized within states, which describe collections of mappings that hold true when the state is active. And finally, the last component is event-driven transitions that enable state change. So transitions can occur on a variety of different triggers, including stylus events, great, geometric events, and intervals of time. And individual transitions can also contain actions, which are essentially just discrete methods called once when the transition occurs. We chose this combination of mapping, states, and transitions because this set provided an expressive representation for integrating procedural and manual control, while also offering a way to offer approachable starting points. And our work here builds off prior research in integrating states and constraints for interface behavior programming. Our interface itself is divided between a pressure-sensitive tablet and stylus and a desktop, laptop, or monitor. And these are structured to separate the functionality. So the programming environment is for tool creation, and the drawing environment is for tool application. And we designed it in a way so that the artist could actually use the drawing interface independent of the programming environment. The artist uses the tablet to author artwork, and the system contains a set of analogs to traditional bitmap art drawing tools. And then the desktop interface contains a visual programming environment where artists can drag out components and use them to author brush behaviors. So we chose to develop dynamic brushes as a visual language to support easier entry. And as mentioned before, visual languages can be more discoverable and encourage exploration. But we also chose to avoid relying on a purely direct manipulation system because of our focus on tool development. Tools represent generalizable, abstract behavior that's different from the artwork itself. So a purely concrete representation or concrete system seemed inadequate. So quickly, I'll demonstrate some of the sample applications of our system. Simple programs can be created that replicate the functionality of basic bitmap brushes found in traditional drawing software by simply using a single state to map stylus position to brush position. But these traditional brushes can quickly be turned into unconventional brushes. For example, a brush that modulates a scale with a square wave generator, creating this undulating pattern. This is just adding one additional mapping and a generator to produce this effect. You can also automate the production of shapes in dynamic brushes through the use of timers in time-driven transitions. So in this brush behavior, a looping transition is created to a state that maps the brush radial properties to generators that enables the automated drawing of pinwheel, star, and scribble-like radial patterns wherever the stylus is touched to the canvas. Automating portions of the drawing process provides artists with new opportunities to enact precise manual control over specific properties. So here, a timer-driven brush is automatically drawing a wave pattern across the canvas, while the artist uses the stylus to manually modulate the heading of the brush and the diameter of the stroke. And then one of the most powerful aspects of programming in applications of art is that it can be used to perform multiple actions simultaneously, leading to the production of intricate generative artwork. And dynamic brushes enable similar effects by using one brush to generate instances of new brushes. This is facilitated through the spawn action, which is a method that enables a brush to generate a set number of instances of any other behavior, including its own. The spawn action enables artists to combine timer-driven behaviors with manual effects to augment hand-drawn lines with procedural effects, so in this case, a drip brush. And this brush behavior is created through a parent brush that follows the stylus and on a regular timer interval spawns a single child, which draws downward autonomously on its own timer. Oh, kind of went through that video quickly. So you can see the full program here. Okay. So for the sake of time, I'm not going to talk in detail about the evaluation we conducted of dynamic brushes. I'm going to focus instead on some general takeaways from the system. But we evaluated the system in a manner similar to Para, where we tested it with two artists working with the system over an extended period of time. But in closing, I'd like to return to the objective I presented at the onset of this talk. The goal of developing procedural systems that support professional artists across different disciplines, communities, and cultures. And so with my last few minutes, I'll briefly summarize the key takeaways from both Para and dynamic brushes that I believe provide pathways to achieving this objective in other domains of artistic production. So first, this idea that building systems, it's important to build systems that integrate support for both procedural and traditional expressiveness. Programming is a powerful tool for artists if it's presented in a form that preserves established forms of expression in a given domain. And what characterizes something expressive in a traditional artistic domain is often fundamentally different than conventional notions of expressiveness in programming. And there can be huge dividends in artistic expressiveness in aligning a programming environment with manual control while retaining a simple programming model. Some general principles that I've leveraged is to aim for incremental learning by thinking about a small number of primitives and also what's possible without knowing the full extent of the system. And also to prioritize forms of manipulation and interfaces that support traditional forms of expressiveness. And finally, to consider the workflows supported by a given system in addition to the types of outcomes it enables, and think about how they align with or diverge with how artists work in a given field. For example, structured versus freeform, or relational versus formalized, or concrete versus abstract. Another takeaway is that it's useful to leverage real-world applications and iterative design to inform the programming model of a system for artists. One of the main challenges in developing any domain-specific programming system or language is that it's very difficult to build the domain knowledge needed to have the right model. And this challenge is exacerbated in domains with tacit and intuitive and sometimes contradictory practices like art. So my work demonstrates that by using real-world application and iterative design to inform the programming model itself, you can build key insights that demonstrate how to design domain-specific programming models and environments. So some of the more specific benefits of this approach is that it can maintain focus on practical and desirable creative applications. It can also demonstrate how the system scales to extended practice and production. And then finally, most importantly, it can help to address the challenge of understanding how to develop programming models for a domain where people have no prior experience programming. So one of the challenges with artists is that because they're thinking intuitively and tacitly, they often lack initially the language to explain to you the types of how to convert those ways of thinking and ways of working into formal or generalizable principles that can actually be applied to a programming model. And actually working with them iteratively while you're developing the system helps them to build the language and communication ability to communicate programming primitives that might be helpful for them. And then lastly, creative applications of computation are dependent on providing people with avenues to extend, modify, and write their own software. Therefore, when designing for artists, it's important to build systems that scaffold end-user software extension and development. And doing so enables systems to support a greater variety of outcomes. And it also supports the development of functionality that directly corresponds with personal workflows and styles. Once again, this is something that's very important for artists as end users in particular, because they often have very refined workflows that they developed for their own practice. And finally, it can lead to a greater variety in the range of tools that are available for the community as a whole. So often artists, like other programmers, release tools they've used in their personal practice as open source systems for others to make use of, which can benefit the community as a whole. So in general, wrapping up, creativity is about making something new. And programming is a powerful medium for creative discovery and making new things. And I like to conclude with this quote from one of the other artists I interviewed, where he talks about the practice of working in programming and incorporating that in making art, where he says, "Working in the digital media field necessitates walking a line between creating work which is conceptually interesting, but also carves out a new aesthetic. And as an artist, you have to find the edges of the box and break it constantly." So in recognition of the diversity of human creativity, I'm trying to strive for equal diversity in the range of programming tools that people have access to and the variety of ways that people can approach making new things with computers. Thank you. Sorry.
Maybe Ron, if he's already here, can start setting up for the next session.
So it's a short question. For both systems, did you also come up with textual representation of the same programming, basically, the programming language?
Not to the extent. Let's see. Technically, yes, for Para, in some of the initial iterations we explored, we also had a separate textual representation. But towards the end of the design practice, we moved away from that because we really wanted to push ourselves to try to do as much as possible through direct manipulation. So we actually tried to avoid that as a design constraint. But something we're looking at in the future is actually now there's some relationships in Para that actually would really benefit through having a textual representation to be able to describe them. And so we're actually looking now at adding in a textual representation that builds on the declarative model that's initially structured around direct manipulation.
Hi, I was wondering, are you familiar with the JetBrains MPS tool?
I'm not.
Okay, maybe you should look it up because, or you can look it up because it's pretty interesting. It allows you to represent a program in a very abstract manner and then write an interface that directly manipulates this. It's used by the whole JetBrains IDE tools to create a AST, and then you can manipulate the text. So it's
bi-directional, like a linked representation?
So no, it's actually it's a representation of its own, which then they use to represent text for their toolings, for the commercial toolings. But it's also more in an abstract form. It has been demoed. Some demos show how you can program basically a table, which is completely non-textual. Well, it is textual, but it's not textual in the sense of a stream of a linear stream of characters. So that might
I'll
be
check it
interesting.
out.
Yeah, please.
Sounds really
It's
relevant.
also open source, so you can.
Great, thank you.
Yeah, I think that unfortunately we are running out of time.
Come find me later if you have questions.
Thanks for reflections.